If a missile were launched right now, you would not see it. You would not hear it. But somewhere within seconds, a radar array would. Long before modern interceptors and space-based tracking systems, the survival of the United States depended on one brutal question. Could we see the strike before it arrived? In the frozen silence of the Cold War, massive radar stations rose from Arctic tundra and remote coastlines, scanning the curvature of the Earth for Soviet bombers and intercontinental ballistic missiles. These were not just antennas. They were the first line of survival in a nuclear standoff where minutes meant civilization. Engineers fought physics itself, pushing radio waves beyond the horizon, calculating trajectories at unimaginable speeds, building a shield not of steel, but of detection. What began as a desperate race to avoid surprise became the foundation of modern missile defense. Today's layered systems, capable of tracking hypersonic threats and guiding interceptors across continents, are direct descendants of those Cold War experiments in early warning. This is the story of how radar transformed fear into advantage, how seeing first became deciding first, and how the invisible networks built during the Cold. If a missile were launched right now, you would not see it. You would not hear it. But somewhere within seconds, a radar array would. Modern missile defense is often associated with sleek interceptors, space-based sensors, and advanced tracking algorithms. Yet its origins lie in an era of vacuum tubes, rotating antenna dishes, and frozen outposts in the Arctic. During the Cold War, survival depended on one brutal reality. The nation that detected first would decide first. The early years of nuclear rivalry between the United States and the Soviet Union forced military planners to confront an unprecedented. In the late 1940s and early 1950s, radar technology was still evolving from its World War II foundations. It had proven effective against aircraft, but intercontinental ballistic missiles presented an entirely different challenge. Bombers flew within the atmosphere and could be tracked along predictable paths. Missiles traveled at extraordinary speeds, exiting and re-entering the atmosphere, reducing warning times dramatically. The United States began constructing a vast network of early warning systems stretching across North America. Installations across Alaska, Greenland, and northern Canada formed what became known as the Distant Early Warning Line. These radar stations were positioned strategically along the most likely polar routes Soviet bombers would take. The Arctic, once seen as a remote and hostile frontier, became the front line of detection. These radar systems were massive, mechanical, and relentless. Giant antenna arrays rotated continuously, scanning for anomalies against the curvature of the Earth. Engineers confronted atmospheric interference, signal degradation, and the limits of line-of-sight detection. Because radar waves travel in straight lines, the Earth's curvature limited how far traditional systems could see. To overcome this, scientists experimented with high-frequency over-the-horizon radar, bouncing signals off the ionosphere to extend detection ranges thousands of miles. It was an extraordinary fusion of physics and military necessity. The goal was simple but unforgiving by time. Time was everything. In a nuclear exchange, even a few additional minutes could mean the difference between retaliation and annihilation. Early detection allowed Strategic Air Command to launch bomber aircraft before they could be destroyed on the ground. It allowed missile crews to prepare counterstrikes. It allowed political leadership to assess whether an alert was real or false. Radar became not just a tool of awareness, but the backbone of deterrence. Without credible early warning, nuclear strategy collapses into blind panic. The Soviet Union developed its own intercontinental ballistic missile capability in the late 1950s. The urgency intensified. The launch of Sputnik in 1957 demonstrated not only space capability, but missile reach. If a satellite could orbit Earth, a warhead could traverse continents. In response, the United States accelerated development of long-range radar systems capable of tracking objects in space. Massive radar complexes were constructed, including phased array systems capable of steering beams electronically rather than mechanically. This allowed near-instantaneous adjustments in tracking direction, increasing accuracy and reliability. The impact on strategic doctrine was profound. Nuclear deterrence relies on second-strike capability, the assurance that even after absorbing a first attack, a nation can retaliate decisively. Radar networks made second strike credible. They provided warnings sufficient to launch submarine-based missiles, scramble aircraft, and prepare command structures. Without early warning, the temptation to adopt a launch-on-warning posture becomes overwhelming and dangerously unstable. Radar allowed for measured response rather than immediate panic. As technology advanced into the 1960s and 1970s, radar systems became increasingly integrated with computer processing. Massive mainframe computers analyzed incoming data streams, filtering noise from potential threats. False alarms were inevitable. Atmospheric disturbances, solar activity, and even flocks of birds occasionally triggered alerts. Each false signal forced refinements in filtering algorithms and redundancy protocols. The stakes were existential. An incorrect reading could escalate into catastrophe. As a result, redundancy became central. Multiple radar stations cross-verified data before classification as a genuine threat. The evolution of radar also influenced the development of anti-ballistic missile systems. If incoming warheads could be tracked accurately, interception became theoretically possible. This concept led to the development of early missile defense programs such as Nike Zeus and later Safeguard. Though these systems faced technical and political limitations, they demonstrated the connection between detection and interception. Tracking accuracy determined interception feasibility. Radar resolution determined discrimination between real warheads and decoys. By the 1980s, radar technology had matured into phased array systems with no moving parts, capable of scanning vast sectors of sky simultaneously. These systems fed data into increasingly sophisticated command networks. The Strategic Defense Initiative, often referred to as Star Wars, expanded the concept further by proposing space-based detection and interception layers. While many elements of SDI remained experimental, its underlying principle, layered defense built upon early detection, reflected decades of radar evolution. The Cold War ended, but the architecture of missile detection did not disappear. Instead, it adapted. Modern missile defense systems, such as ground-based interceptors and Aegis ballistic missile defense, rely on integrated radar networks capable of tracking multiple targets simultaneously. Sea-based radar platforms extend coverage into contested regions. Space-based infrared systems complement ground radar, detecting missile launches through heat signatures. Yet the logic remains unchanged from the Arctic radar lines of the 1950s. Detection first, decision second, interception third. The emergence of hypersonic weapons in the 21st century has once again intensified the race. Hypersonic glide vehicles travel at extreme speeds and maneuver unpredictably, complicating tracking. In response, radar systems are evolving to detect lower-flying, faster-moving threats. New generations of over-the-horizon radar, combined with satellite constellations, attempt to recreate what Cold War engineers achieved decades earlier, extend warning time against an evolving threat. The influence of Cold War radar extends beyond hardware. It shaped strategic thinking. It institutionalized the belief that technological superiority in detection can offset numerical disadvantage. It reinforced the concept of layered defense. It proved that physics, when harnessed effectively, can shift geopolitical balance. Nations today invest billions in early warning because the Cold War demonstrated that awareness is power. Perhaps most importantly, radar transformed the psychology of nuclear confrontation. Knowing that incoming missiles could be detected reduced uncertainty. Reduced uncertainty stabilized deterrence. Stability, even fragile stability, lowered the likelihood of accidental war. The silent rotations of Arctic radar dishes contributed to decades of uneasy peace. Modern missile defense, therefore, is not a sudden innovation of the digital age. It is the culmination of a 70-year evolution that began in frozen outposts scanning empty skies. It is the legacy of engineers who fought curvature, atmospheric distortion, and computational limits to create time where none existed. Every interceptor launched today depends on that foundation. Every satellite tracking system echoes those first experiments in early warning. The Cold War radar lines were never glamorous. They were isolated, mechanical, and often hidden from public attention. Yet they formed the backbone of a strategic shield that still defines global power balance. The ability to see first remains the ultimate advantage. In a world where missiles travel faster and threats grow more complex, the lesson endures. Survival begins with detection. And it began in the Cold War, when radar transformed fear into foresight and built the foundation of modern missile defense. Modern missile defense began during the Cold War, when the United States needed a way to detect Soviet bombers and ballistic missiles before they could strike. To solve this, massive radar networks were built across Alaska, Greenland, and northern Canada, forming an early warning shield that extended detection thousands of miles beyond U.S. borders. These systems allowed the U.S. to track incoming threats in real time, providing the critical minutes needed to respond and maintain nuclear deterrence. Over time, radar technology evolved from basic rotating antennas to advanced phased array systems capable of tracking objects in space. This foundation made modern missile defense possible, including today's ground-based interceptors, sea-based defense systems, and satellite tracking networks. The core principle remains the same. The nation that sees first decides first. Cold War radar didn't just protect against attack. It shaped the entire structure of modern missile defense.